Right? So like you have graph traversals. That's like one approach to solving problems. Dynamic programming is another approach to solving problems. And the best way to understand it is you see a few examples of it, and then you try to come up with some of your own. So I'll give you homeworks and assignments that will sort of test that. But before even telling you about what dynamic programming is, it's useful to consider a class of algorithmic problems that are very, very prevalent, in computer science and in a lot of applications, which I'll refer to as discrete optimization problems. Okay, so what is a discrete optimization problem? The way to think of it is like there is a collection of n items or choices. And we need to pick a subset or an ordering on the n items or choices that maximizes or minimizes some objective. Okay, so that's what I've written in English. I'll tell you what I'm just going to give mathematical notation. So I use this basically as a shorthand for this. So this is just saying that the first n natural numbers, which you can think of as indexing some choices. So there are n choices you need to make, like n items you need to pick. And so this is like the universe of choices that you have. This is the set, or I should say family, of all subsets of this. So this is like all possible choices you could make. So it could either be that, or sometimes you also have this set, which is the set of n of the n factorial permutations of this. Right? So these are sets, and usually what you want to do is you want to compute. So I'll say, suppose you have some function, maybe even to real numbers, and you want to compute, let's say, the maximum of s over f of s. So this is usually your problem setting. Sometimes this could also be a function from permutations to that. So what is this saying? It just says that you have some function on the set of all subsets, and you want to maximize this function or maybe minimize this function, depending on your objective. Okay? And I'll say like a large fraction of problems that people are actually solving in practice, in industry, in research, in academia, often boil down to some version of this. It's called a discrete optimization problem because the function is discrete. Right? It's not a continuous function that you're minimizing. And so, what is the size of the domain of this function? This f. What's the size of the domain? Any? Yeah? It's 2 to the n, right? Like in the first case, it's 2 to the n. In the second case, it's n factorial. Right? So the number of options that you have is huge, is exponential. So the number of options, so think of the domain size or the number of total possibilities is either 2 to the n or n factorial. Okay? And usually in these settings, and I'll show you, we'll talk about some of these settings, but in these settings, given S, f of S is easy, which I mean it's efficient to compute. So like, I'll give you sort of an advertising example, although there are like tons of others. So the advertising example is in your typical social network, right? Someone who's advertising has a budget. So they'll say like, they have X amount of dollars to send ads to. Each person they send an ad to costs money. So they'll say, given this is my budget, what is the subset I should send ads to so that they will spread it to their friends the most? Right? So you have some kind of choice where you have to choose some people to either send a message to or to do something, and then you have to figure out what is the best way to do it. Another version, which people study if you take the power grid. Well, this is often studied from an adversarial perspective. But let's say you have the power grid, and people are trying to study how resistant is this to failure. So they'll say, what is the minimum number of nodes I need to remove so that the power grid gets disconnected? Right? So again, your choice is there are lots of nodes, and you have to look over all possible subsets of nodes potentially. But that's your function. Right? So the number of choices you have is exponential in the size of the input. So is this sort of making sense? Yeah? Or if you've seen something like minimum spanning trees before, that's also a discrete optimization problem because you have to choose some set of edges. So a lot of these questions are about choosing a set of objects. Now, if I say, like, give me an algorithm to solve such a problem, you'll say there is an easy, well, I shouldn't say easy, I should say trivial, exponential time algorithm, which is just try all choices. Right? So you have some number of choices for this function, so you could just try all possible choices. Make sense? Before I get there, question. Is for sufficiently large n factorial bigger than 2 to the n? Yes? No. Not even giving you maybe. Think of n that is large. Maybe n more than 5, 6. Is n factorial bigger than 2 to the n? You have to dig up the recesses of your brain that may have held some discrete math knowledge. Right? In some corner is probably there. Yeah, what's the answer? Yeah, you should be more confident. The answer is yes. Okay, now I'm going to give you a hard one. Is n factorial more than 2 to the n squared? It's harder. Yes? No? There is no yellow option. It's only red or... There's no maybes, sorry. You can't cheat your way out of that one. Okay. Most of you say red. You're wrong. Why? Why did you say red? The answer is no. Why? Yeah?
Because you can move the 2 down above the n to make it 2 to the 2n.
No. It's 2 to the n squared, right?
Oh, okay.
2 to the n squared. Does that change your decision?
Yeah, sorry.
Sorry. It's 2 to the n squared. Yeah?
Wait for red versus blue.
Forget that. This is the question.
Just to answer the question. question.
Just answer the question.
I think it's no.
Why?
Because, if you imagine like n factorial,
Uh-huh.
1 times 2 times 3, so on.
Correct.
But 2 to the n for a given n should be larger than the equivalent like factorial number.
Well, we said that n factorial is already greater than 2 to the n. The first one is correct.
Yes.
Why is the second one?
Why is the second one no?
Yeah.
Yeah, because I think that like 2 to the n squared means that the thing you're multiplying at the end of it should be greater on the 2 to the n side rather than the factorial side, because like 2 to the n squared is okay.
Yeah?
I think that like in n factorial, the largest product of numbers is going to be n and n minus 1.
Sure, n minus 1, n minus 2, so on and so forth.
And in 2 to the n squared, the largest product of two numbers is going to be much bigger.
But you're multiplying many numbers, right? So the largest of the, no? Yeah.
So if we're to consider like n plus 1, if you're considering n factorial times n plus 1, so you're scaling it by that much.
Okay.
But when you're considering 2 to the power of n plus 1 squared,
Good,
now
yeah.
you're scaling it by like 2 times n plus, or 2 times.
Yeah, that's fine. Yeah, you're actually scaling it by 2 to the n almost.
2 to the like 2n plus.
2 to the 2n plus 1. Yeah, okay, good. That's a sound reasoning. But I'll give you a more direct reasoning. Just take logs on both sides. Take log base 2, right? So what do you get on log base? I'll write this. Sorry, I didn't even want to talk about this, but anyway, maybe we should just. Okay, so why is the case? Whenever you see things with exponents, take logs. That's why they're there. Okay? So what you're getting is log base 2 of n factorial versus log base 2 of 2 to the n squared. Now this guy is easy, right? That's just n squared. What is that? Okay, good. So this is basically, if you apply the log formula, you get log base 2 to the I, where I is going from, let's say, 2 to n. Yeah? Okay. Now what? Yeah, what is that thing on the left? Yeah, but it's a sum of n things. What is it at most? You're summing n things. What's the largest thing that you're summing? Largest thing in that sum? Log base n? Log base 2 of n? It's log n? How many things are you summing? N minus n, like roughly n things. So it's at most n log n. So most n log n. And that other thing is n squared. Now, n squared is much bigger than n log n. Okay? Right, this thing is at most n log base 2 of n versus n squared. And if you remember from merge sort and all of those things, right? Insertion sort takes n squared, merge sort takes n log n. And you know that merge sort is faster. So it's n log n. So you take logs. Okay. Anyway, the reason why I said this is n factorial is like exponential. So actually, we know that n factorial is actually roughly, what this says is it's roughly, I say 2 to the theta n log n. I say theta, it's technically like, you should take natural logs, and I think it's, so anyway. That's about what it is. It's like 2 to the n log n. Okay. And for those of you who are interested in the math, this is actually called Stirling's approximation. It's actually even stranger. It's I might as well write this down. So it's known that n factorial in the limit is square root 2 pi n divided by e to the n. Which, if you think about it, is completely insane, right? Because n factorial is just counting permutations. It has nothing to do with circles. But then the formula actually has pi in it, in the limit. Okay. Anyway, so I don't even know why I said this, but let's go back. Why all of this stuff? A lot of discrete optimization problems are about ordering or maximizing over sets. And this, in general, is exponential. And so, for discrete optimization problems, there is a simple exponential that is in the size time algorithm. So just to give you a sense of what is an exponential time algorithm, so think of your time is like 2 to the n, okay? So if n is equal to 20, could you solve this on a computer? Say the running time is 2 to the n. What is 2 to the n roughly? Where n is 20? Yeah? A million. It's about a million, right? Because 2 to the 10 is 1,000. 2 to the 20 is a million. Million, you could probably solve this. But if you say something like if n is 50, or maybe n is 100, there is no way you could solve this, right? 2 to the 100 is, I think, it's close to the number of protons in the universe. It's probably more than the number of seconds or maybe milliseconds that the universe has existed, like that long, right? So 2 to the 100 is impossible to solve. But 2 to the 10, this is possible, even on your laptop. This is just impossible. And by impossible, I mean impossible no matter how much compute you can afford to throw at it. So if you ever end up with a problem, a discrete optimization problem, and you try to solve it just directly, you'll often end up with an algorithm that just will not scale. And so one of the questions is there a polynomial time algorithm? And the methods that we're going to talk about maybe the next half of the course are all about methods to do that. So you have a discrete optimization problem. So one is you formulate your problem as a discrete optimization problem, and then you try to use a technique like dynamic programming or greedy algorithms to solve it to get something that is polynomial time. By polynomial time, I mean something that looks like the running time is going to be like n squared, n cubed, n log n. Now, even things like n squared and n cubed can be quite large in practice, but it's definitely better than 2 to the n. Okay? So this is, and so dynamic programming is a technique to help you get these runtimes. So the way really to think about dynamic programming, I'm giving you all this sort of preamble because I can throw out a bunch of algorithms at you, and I can explain them and you'll understand them. But what is the point of it? The point is, in general, if you see an algorithmic problem, and if we're able to frame it as a discrete optimization problem, so you model it as a discrete optimization problem, then one of your first tries is, can I solve this with dynamic programming? Can I solve this with the greedy algorithm? So that's how sort of you view these things. Just like when you have a graph problem, if you have some problem that you convert to a graph problem, the first question you ask is, can I use BFS or DFS to solve it? Right? So that's sort of the way that I want you to think about these things. And for what it's worth, I don't necessarily want to get too much into interview prep, but that's sort of the way that if you want to show someone that you understand, that's how you do it. You say, I'm going to frame this as a graph problem and use these and try these methods. I'm going to frame this as a discrete optimization problem and try out dynamic programming. Right? That's sort of how you want to convey your thinking. Okay, so I'm going to start with a classic example of a dynamic programming, which maybe some of you have seen before. It's called the knapsack, or technically the 01 knapsack problem. Does this sound familiar? Yes, no? Raise your hand if you've seen 01 knapsack. Okay, so most of you have seen this. So maybe we can go over this pretty quickly. Okay, so let me talk about what's called a packing problem. So we have n items, right? Each item has a weight, and again we'll say this is an integer weight, and an integer value, which I'll call vi. So every object has a weight and a value. And so let's say I'm just drawing these as n objects. And so you have these arrays, wi and vi. And then what you have is you have something called the knapsack. And the total capacity is capital W. This is often called the capacity of the knapsack. So it's like you have this bag of W and you have a bunch of items. So what is your aim? You want to pick a subset of items, put them in the knapsack. So the weight of those items should not exceed the capacity. And under that constraint, you want to maximize the value of the things you've picked. Okay? Yes?
Is it kind of like the rod cutting problem?
Like what?
The rod cutting problem?
The rod cutting problem. I don't think so. That's where you have like this thing and you want to cut it into a bunch of pieces and different people take different pieces. Is that?
Or like depending on the length you cut it into, it has a different value.
Okay. No, so that has a similar feel to it. But so if you think about the choices here are like binary for each object. And there it's not really a binary choice between the objects. But you'll see that, a lot of it is dynamic programming based. Okay, so does this make sense? And so have you ever heard of the phrase supply chain? Yeah, sort of. So in the supply chain, they solve knapsack problems all the time. Because you've got a bunch of goods to move from one place to another, and you have a truck with some bounded capacity, and so you kind of figure out which are the items to put in. So actually in the, 70s or 80s, a lot of people who studied these problems ended up building lots of companies that ended up like doing all the supply chain management. So a lot of things about how to move goods from one place to another, which is a lot of what happens in modern economics, is about solving problems like this. So another way that this is phrased is, what is your function? So if S is any subset of n, so S is a subset, I'll say that if the summation of I and S of Wi is less than W, then the value, or the function value, is this, and it's 0 otherwise. Okay, does this make sense? So what I'm saying is, if the set of items you've picked is valid with respect to the knapsack constraint, then I get a value. If it's more than that, then I say the value is 0, meaning that you're not allowed to do it. And you are trying to maximize this function. Right? So this is a discrete optimization problem. Okay, so and the aim is to find S that maximizes f of S. Okay? And so you see that it's exactly a discrete optimization problem. It satisfies all the conditions that I said, which is, one is, of course, the domain of the function is all subsets. But secondly, given S, computing f of S is really easy. Right? If I tell you this is the subset, you can always check the constraint and you can figure out the value. Does that make sense? right? So I'll write this down. Given S, alpha of S can be computed in O of n time. Okay, so so this is easy. So this is a classic example where, again, so brute force, the simple brute force algorithm, the brute force simple algorithm runs in O of n times 2 to the n time. Right? Does everyone see that? Right? Because I have 2 to the n options, and for each option I can in linear time go and check what its value is, and then I just have to sort of compute the maximum. So I could run a loop over all of them and compute the maximum. Right? If I just try all possibilities. Yes?
One question. Could you just explain, S is a subset of n in square brackets?
Oh, so that's just saying that S is a subset of 1 to... This n in square brackets is a shorthand notation for that. It's just saying that I'm picking any subset of the n items. So this is a very common notation that's used in sort of discrete math for that, which is why I want to put that up there. Okay? Okay. For those of you who've seen this, do you remember the solution for this, dynamic programming? Yeah, no, kind of, sort of, kind of. Should I go over it again? Is it worth going over it? Yeah, okay, let's do it then. Okay, so how do you, I mean, I can always, again, give you the dynamic programming solution, but the question is, how do you know that this problem is sort of, or dynamic programming is applicable to this problem? So the first thing that you do is you observe that it has a recursive solution, which is also called a recursive substructure. So suppose I have these n items, right, which I've labeled 1, 2, n minus 1, and n. And the way that I observe the recursive substructure is I say, look, the choice that I really have is, should I add the nth item or not? So I'll say 1. Suppose I choose the nth item. So now what happens? So I decided to actually pick it. I want to sort of come up with a recursive problem. I want to describe what is left as another knapsack problem. So what is that knapsack problem that I have now? So right now, I mean, I've chosen the nth item, right? And I want to make like one recursive call. So assume that I'm trying to sort of develop a recursive algorithm.
Colligated function, but with the set of 1 to n minus 1.
Okay, and there's a change. Yeah?
You subtract from the maximum weight allowed, and you also, you just do that.
Right, so you have to reduce the knapsack now, and you add in the value. So what you lost was knapsack capacity, but what you gained was the value of this. So what I can say is, recursively solve with the knapsack capacity W minus the weight of n, and the items 1 going to n minus 1. And then add in the value Vn. Right, so I recursively solve on whatever is left with a reduced knapsack, then go back and add the value of what I just put in. Yeah? So suppose I do not choose the nth item. Okay, suppose I don't choose the nth item. Well, then it's easy, right? Then I just recursively solve on the first n minus 1 items with the same knapsack capacity. So this recursive feature of the problem, which is often there in many discrete optimization problems, you'll see like you have these n choices to make. Once you make a choice, so it's like this question of should I make the choice or not? And depending on how you make the choice or not, you get a different recursive problem. This is really important to see. Like if you start seeing this structure, that's when you think maybe I can do dynamic programming. And again, sometimes dynamic programming will work, sometimes it won't. But you have to look for that recursive substructure. And whenever you have this discrete optimization problem of this kind, often you will see there will be some recursive substructure. Okay? Okay, so I'm going to write this. So this is now, suppose I do not choose the nth item, then I say recursively solve with the knapsack capacity just W, because I haven't changed the knapsack, and items 1 to n minus 1. And then what do? I just output the maximum of these two answers. Right? So I've seen what happens if I add the item, I've seen what happens if I don't add the item, and then depending on those choices, I see which is the better choice. Right? And so I just output the maximum of these two choices. Okay? So just to give some notation, I'm just going to write this down as a formula. I'm going to use this sort of bold ij to be the set of items numbered 1 to j. And the set of items, with the weights and values, like the collection of those two arrays, right? I'm just sort of treating that as, I'm just saying bold ij is that set. So suppose I want to solve knapsack, in this case something like I, n, w. So this is saying the n items, this is the knapsack weight. So I'll write this out as follows. I'll just sort of write it out like this. So if Wn, that item, actually has a weight that is less than the total knapsack, like if Wn is greater than W, well then there's really nothing to do. I just return knapsack I of n minus 1 in W, because I cannot add it to my knapsack. That's the uninteresting case. This is the interesting part. So I take the max of two things. So I take knapsack of I n minus 1 W minus Wn plus Vn. Sorry, this is getting a bit messy. And knapsack. Sorry, I'm just going to write this out separately. It's too much. knapsack INW. So I'll put down the cases over here. So the first one, it says you take the max of knapsack IN minus 1, W minus little w of n. So you've reduced the capacity, but you add in the value. That and knapsack IN minus 1 W. So you take the max of these if Wn is less than W. If Wn was more than W, then you just do the vanilla knapsack. Does this make sense? This entire thing, this is called a recurrence. So in any dynamic programming problem, like ones I give in the homework, the first thing you would do is you would write down figuring out the recurrence will take effort, but once you figure it out, you will write down the recurrence. Then it kind of becomes clear that, okay, this is how you're going to do dynamic programming using this. Okay? So this gives me also a recursive algorithm. Right? I have an algorithm that comes straight out of this. And so this gives a recursive algorithm. And so a question is, what is the running time? Is it does the algorithm make sense? I just call it recursively. And I haven't given the base case, but the base case is easy, right? Base case is one item. If you have one item and a knapsack, you just check, can you add it or not? And if you can add it, go ahead, otherwise don't. Right? So this actually captures the entire algorithm. Is it polynomial time? Is it exponential time? So polynomial time, thing like n, n square, n cubed, something like that. Exponential, think something like 2 to the n. Or is it more than exponential? I'll say 2 to the n square, whatever. Anything which is like 2 to the some polynomial in n. Let's keep it easy. So what is the running time of this procedure? I just told you what the procedure is. Okay, now there's a lot more disagreement. Some say it's polynomial, some say it's exponential. So why is it? Why? Does anyone have any reasoning for their answer? Yeah? Yeah, go ahead.
You're making constant progress towards basically emptying the set of elements that you're looking at when you're trying to fill the knapsack.
Okay, but you also have two choices at each time. And you're choosing, so does the algorithm make sense? Like you would basically call all of these functions, right? So you have to call knapsack. I mean, if you're in this case, you have to call both these functions. So you're right that you're making progress. Okay, yeah.
I think it could be like a factorial problem, because every time it gets one shorter.
Right.
So that's not exponential, and that's not more. Well, that could be.
Okay. You tell me. Okay. Yeah?
At each step we call knapsack twice.
Yes.
So, and then each of those knapsacks calls it twice and so on, so it's exponential.
It's exponential. Right? It's exponential. Actually, why? Because there are 2 to the n function calls. Each one calls, you're right that you're making constant progress, but the cost of that constant progress is 2 calls. And those 2 will make 2 calls and so on and so forth. So if you write down this recurrence and you run it, you end up back at the brute force algorithm. If anything, if you really think about this, if you uncoil this procedure, it's trying out every possible subset. So this will often happen that you think you come up with a clever way of writing something, you write it down and you're like, wait, this is actually the same dumb algorithm. Right? And you'll see this happens often, but this is useful because you can say, if I run this directly, I get an exponential time algorithm. Now let me see how I can optimize things over here to make it polynomial. And that optimization is going to lead to dynamic programming. So this is good. So now that we've agreed that you're making too many function calls, some feels like the only way that you can improve on it if you don't make all the function calls. Somehow you have to cut down on the number of recursive calls made. So we're at almost 8:45. So I'll say something and then we will. So actually in the worst case, like if you don't assume anything about W and anything, then actually it's not known whether you can do this in polynomial time. If you could actually solve this in polynomial time for all settings, you would prove P is equal to NP. So, which is highly unlikely. So, okay, so what I'm going to say is suppose W, which is the total weight of the knapsack, is not too large. What I'm just saying is that W is polynomial n, which is a pretty reasonable assumption for many settings, right? Like the weight of the knapsack, this is some reasonable number. It's just polynomial, which often happens. So look at these calls. What does each call look like? So if you look at knapsack, each call looks something like this, right? In this recursive procedure, all the calls are the form where the first argument is some set of items. The second argument is the size of the knapsack, and it's an integer. How many options are there for the first argument? How many possibilities are there? How many? What are the yeah, someone said, yeah? N, right? Because, we're saying ij, so you can either, remember, ij is the set of items numbered 1 through j. So there are only n possibilities. J goes from 1 to n. Because the way we're doing our recursion is we're kind of peeling off one item at a time. So the remaining stuff is the argument, and there are only n possible choices for that argument. Right? Yes, no? Okay, so there are n choices for this. How many choices are there for the second argument? What is the maximum value that I could take? Yeah? W. So the only choices for the second argument are 1, 2, 3, going up to W, right? This is an integer. So the choices over here were basically I1, I2, I3, In. So there are only n times W distinct function calls in the recursive algorithm. This is the key. So there are two fundamental points about dynamic programming. First was the recurrence. The second observation is the fact that even though you're making tons of function calls, there aren't that many different choices for the arguments. So what does that mean? What is the recursive algorithm doing that's wasteful? Yeah?
Repeating same calls again and again.
Exactly. It's repeating the same call over and over again. So it's like it's making a function call, and then it's going to make the function call again. So it's wasting an exponential amount of time computing something that has already been computed before. Once you observe that, then you can set up dynamic programming. Yeah? Yeah, okay. Actually, you know what? Let's take a break for a couple minutes, and then I will repeat that after the break. Right? 8:45, so 8:48. Yeah. Okay, so let's get back. So I'll just recap what I said. So first is there is a recurrence for the knapsack problem. So the recurrence just says that to solve the knapsack on n items with a capacity of W, in the simple case where the last item is actually larger than the entire weight of the knapsack, you just throw the last item away. Just make one recursive call. So that's easy. The interesting case is the first one. So if you have an option, you can either choose to keep the item, in which case you get knapsack of n-1 items with a reduced capacity plus the value, or you throw the last item away and you just get, you get the knapsack with n-1, and you keep the same knapsack and you have n-1 items. And so you choose the maximum of those two. This gives you a recurrence. If you run this naively, you get an exponential time algorithm, right? Because every function call makes 2 children calls, each of which will make 2, so on and so forth. This recurrence, if you unroll it out, is just trying all possible subsets. The way we observe that there is an improvement or a potential for improvement is we say, well, suppose the second argument is an integer, which is not too large, but it's polynomial. So it could, by not too large, it's not exponentially large. It's a polynomial. Then what you observe is that if you look at the possible function calls that are there aren't that many, because there are only n choices for the first argument, and there are w choices for the second argument. So there are only n times w distinct function calls in the recursive algorithm. Another way of saying this, so I'll draw this out, is let's go ahead and look at this, let's look at the recursion tree of that simple recursive algorithm. So there are 2 to the n nodes in the tree. And let's just say for each node, I just write out what the arguments of that function call are. So, here it's basically in w, maybe it's in minus 1 w, this is in minus 1 some w prime, right? Because the knapsack would have reduced, and this gives you in minus 2 something else, so on and so forth. So there are all these choices. Even though there are 2 to the n nodes in the tree, there are only n times w distinct labels. What this means is if you go down further into the tree at some level, like many of these would have the same label, meaning that it's the same function call that's just being duplicated in the recursion tree, right? So instead of calling it so many times, you should only call it once and store the value. And if you did that, then next time you see the same thing, you don't have to make further recursive calls from there. Does that make sense? So this is making 2 recursive calls, but if you solved it once, you don't have to make these ever again. You don't have to go down the tree, down this recursion tree again. So what you do is you basically save on the recursive calls. Does this make sense? So this feature, so I'll give you sort of the term, this is referred to as overlapping subproblems. So for dynamic programming, you start with a recurrence. This leads to a recursive algorithm. And then you observe plus overlapping subproblems, which is the same thing as saying that how many number of distinct function calls is small. If you see both these features, then that leads to dynamic programming. So now I just have to tell you how to put it together for the dynamic programming. Yes? Yeah.
You keep on saying, like, okay, this is dynamic programming, this is dynamic programming. So is dynamic programming the addition of these two, or is it just finding also, like, the exponential runtime?
No, it's really it's the polynomial time algorithm I'm going to give you that's dynamic programming. So right now I haven't told you what the dynamic program is, but my point is once you observe these, whenever you see both of these features in a problem, that's how you know you can do dynamic programming.
Questions. First, that's always a condition to be dynamic programming, or there could be other conditions different than overlapping?
So usually, whenever you have a dynamic program, you'll have these features. Pretty much. I think I think for the sake of this course, that is a good statement to say. Yeah.
So at the end, the complexity would be O of n times W.
Yes. Or O of, it's going to end up being O of n times W.
And third question, how do you implement that? Like you have like a...
I'm going to show you right now. That's what I'm going to do. So the next thing is I'm going to basically show you the dynamic program and show you how to implement it. Okay, good. So is this clear? So now let me tell you how to set this up as a dynamic program. Like what is the dynamic programming here? So once you see these features, so again, I want to reiterate, the way we started is you start with the recurrence, you look at the recursion tree, you say, oh, this is exponential, but you observe overlapping subproblems in that recursion tree. Once you observe these, you now are set up to build the dynamic programming solution. And so this is how it works. Oh, I actually forgot to put page numbers, so I should do that. 24. Sorry. 5. 6. 27. 28. That is 29. Actually, that's 9. Okay, so how do we set up the dynamic programming table? So we'll go back to this part here. So remember, we broke it down into recurrence, which has this recursive call structure. So the table is now going to have two parts to the table. It's just going to have all possible arguments. So this is the what I call DP dynamic programming table. So on one side, I'm going to put the item or the item list, technically, the item list. And the other, I'm going to put the knapsack capacity. So I'm going to write this, I'm going to write down all possible arguments in this table. So it's W, W minus 1, W minus 2, W minus 3, going all the way to like the base case of 0. That's the knapsack capacity. Here I'm going to put items list, so it's the first n items, n minus 1, n minus 2, all the way down to, let's say actually 0 items, just as a base case. It's like you have nothing. Okay? So instead of the recursion tree, I'm actually going to build a table of all possible arguments to this function. That's my table. Okay, so this is how you implement it. So this right now, to answer the questions, is the dynamic programming part. So we build this table. So this we could store as a matrix or a two-dimensional array. So first what you do is so what we're going to do is we're just going to populate the values of this table. And we're going to do a bottom-up filling of this table. So down here, we know that the values are all 0. Right? Because that means that either you have no knapsack or you have no items. What we need to do is to figure out, suppose you want to solve this. Suppose you want to find out what goes here. How many cells of the table do you need to look at? Put the recurrence again in front of you. If you want to find out what goes in that table, how many? 2, right? And where do those 2 entries lie? Yeah?
To the right and down.
To the right and below, right? So they're basically going to be below this and to the right. So in other words, they're going to lie it's going to be maybe something there and actually this one. So these are the 2 entries you need to look at. And then of course you have to do some calculation there. But you only need to look at 2 entries in the table. And those entries lie to the right. So how would you fill up the table then? Yeah? Bottom up, right to left. You can actually just go column by column. Right? In each column, you basically just go, you can actually go either way, up or down. But exactly, so you can fill up column by column. Right? So it's really neat, right? So instead of actually running this whole recursive procedure, what you do is you build the table and then just fill up the table in order. Okay? And so the running time is O of NW. The space, I should say it's theta in this case. I mean, it's basically NW, right? Because every entry in the table you can fill up by looking at 2 entries. Right? To fill up a square, to fill an entry, we only need 2 values that are to the right and below. So this is really important because this is then how you do the implementation. Because now you know exactly what is the order in which to fill up the table. And so as you fill up the table, you will eventually end up with the value over there. And that is the value of your knapsack. Okay? Questions? Yes?
Why start with, why not flip the axes so that you do go top to bottom?
It doesn't matter. I mean, for me, the way that I think about it is like sort of the entry that you care about is right at the top. Like that's like the first entries you care about because that sort of corresponds more to the recursion, but you could flip them in any way. All you need is an ordering of the entries. So you have to build this table and then you have to figure out the ordering. So what you need over here is the table structure, plus the ordering to ensure all entries get filled. And you can essentially write out this filling up as pseudocode. Right? So I'm just going to, Okay, so by the way, so what this does is give you the value of the knapsack. But how do you figure out what the knapsack should have? Does that make sense? Like, this is just telling you the value, but you actually want to know what to put in the knapsack. Okay, it's not that difficult. Like, you have to do something with this again. Yeah, in the back, yeah? Backtrack how? Yeah?
We could do the same predecessor thing as we did for BFS and have each one point to the ones we used.
Exactly. You can just have, you could set up a predecessor, or what I'll show is you can even set up a Boolean matrix that at each point just tells you, should you look at, each one, there are just two possibilities. Do I take the item or not? And all I need to do is just to put a Boolean value there. Do I take the item or not? I can keep following that down. So I'll just write out a little pseudocode for that. But is this clear? Is this making sense? So I think the best way to learn this so what I will do over maybe the next couple of lectures is to give more examples of dynamic programming. And I think when you see about 3 or 4 at that point, well, I'm tired of showing them and you'll be tired of seeing them. And then I'll make you implement maybe 1 or 2. Right? And when you write the code to do it, I think a lot becomes clear. You solve a few problems. Once you kind of get it, it's pretty straightforward. Like, unlike actually things like traversals and all, which are much more complicated to understand, this is actually much easier once you get the basic idea. Okay. So I am not going to write out the pseudocode for filling up this table. Instead, I'm going to write out the pseudocode for filling up what I call the choices matrix. And you'll see that basically they're the same. So to get the knapsack contents, one can build a Boolean choice matrix that says whether to take an item. And you can also, just as well as suggested, set up a predecessor structure where you basically point to various entries. So you could even put a pointer to the other entry that you have to go to. But I'll set it up as Boolean, but in some cases it's not Boolean, and then the pointer makes a lot more sense. Okay, so I will set up this is 32. The Boolean choice matrix. So I'm just going to call this choice. And again, this has 2 arguments. It has, the knapsack. It has a knapsack constraint and a set of items. And this is how you fill it up. So you basically say, if the weight of the jth item is less than W prime, so I'm going to say, suppose you filled up this matrix. I'm just going to make it easier for now. I'm going to refer to this matrix as the knapsack matrix, so the KS matrix. So if the KS matrix I j minus 1 W prime is, let's say, greater than the knapsack with j minus 1 W prime minus Wj plus Vj. So if the knapsack value, finally. Then choice of I, j, W prime should be is it true or false? So think of this matrix as indicating whether you should pick that item or not. Give you a few moments to ponder and tell me what the answer is. Question or answer? Question. Answer. No. So I give you Post-its for a reason. Okay, what is the answer? Is it true or false? Yeah, it's okay, so it seems like there's some confusion in the answers, but it's false, right? Because if you're getting a better knapsack value by not taking the item, then you should not pick the item. So this is false. Else, this is equal to true. Does that make sense? So the else basically says that it was beneficial to pick the item, so you should set it to be true. And the other condition is, of course, if Wj is greater than W prime, then choice Ij W prime is what? True, false? Yeah? False. Okay? Yes, no, everyone sort of follow what happened, right? So then in this case, it's false. And so it's just like these, 3-4 lines of code. This will then set up the choice matrix. You have to write another 3-4 lines of code to get this matrix. You could technically build both matrices together, like at the same time. But how you implement doesn't really matter that much. But there is this distinction of having sort of two matrices, one that keeps the choices and the other that keeps the values, which is often convenient. Again, you could fold both of them into one and whatever. But it's conceptually, I like to think of them as two copies, separate sort of structures. Yeah, clear? Yes. Right, so it's essentially just a check. Was it better to take the item or not? And in this case, it's saying it's actually not better to take the item, so you just set it to be false. But if you think about it, this is the exact computation that you're also doing to figure out what this matrix looks like. Yeah?
Instead of using a Boolean, can we just drag the value, like having an array, and if it's true, just put that array and that's it?
I don't think an array would be enough because you don't know which of those chains is going to go back all the way to the top. I mean, you could start here. Okay, I see what you're saying. You're saying start at the top, compare those values, and then figure out should you keep that or not. You're right. You could also do that. You don't necessarily need to keep the array. Yeah. Yeah, you don't necessarily. But the utility of building this sort of choice matrix is now you actually get the knapsack solution for any knapsack weight, all in sort of one go. How you want to exactly implement it is really up to you, but it's useful. Again, I think conceptually it's useful to have this view in mind. Yeah.
I guess like when you're applying the knapsack algorithm, are you actually building the KS matrix before you even choose?
So you would, yes, you're actually going to build this matrix, and you're going to fill up the matrix.
Before you even, I guess, go again and then find.
So this is what I was saying. Like you could implement it so that both of them are being done together, right? But because you'll see that this logic that you only need two values to the right and below are still true over here because the only values you need are really to the right and below. Yeah, you had a question? No. Okay. So again, how you want to implement it exactly is sort of, there are options, but the important thing is to know that you're going to construct this table and you're going to fill up the table. Okay, so actually this discussion is useful because while coming here I was thinking like what to give for the next dynamic programming assignment. And now I know. I'm going to actually give out maybe like a really small homework, just like 5 points. It's going to be a fairly simple dynamic programming problem, but I think it's a good exercise so that you'll actually build the table and you'll see how to do it. And then I might actually give a more complicated one to solve as well. Yeah?
So is the point of the choice matrix basically figuring out whether or not you should take a value, whether or not it's the most optimal? Like, is it short-circuiting, basically? Like,
It's basically, if you look at this table gives you the value. It doesn't tell you what the solution is.
isn't the solution the top left?
Okay, so that's the value. It doesn't tell you what are the contents of the knapsack.
Oh, I see. Thank you. That was what I was-
Yeah. Yes?
So to know the value of the knapsack without a separate thing, you have to maintain.
So, okay, so maybe I feel maybe I've over confused this issue. So, let's maybe go back to the knapsack problem. I mean, there are sort of two questions here, which I've kind of buried here. One is to say, find the S that maximizes Fs. And the other question is, find Fs of the S that maximizes Fs. Like, you can either try to find the maximum value of the function or find the argument of the function that maximizes. Does that make sense? Like, there's a slight difference between, do I just want to know what is the best value I get? Or do I want to know what to actually put in the knapsack? Yeah?
So if I understand correctly, then when filling the table based off of that, you choose what the entries are. And the entries are would be the optimal, either S or F.
So this table over here is really giving you F of S. And the choice is, this is like giving you S. Does that make sense? But the logic is identical in both cases. The logic is really the comparison of these two entries and seeing which is better. So, and the right thing to do is you build the FS table first. Then if you want to get S, there are three options. I gave you one option with the choices matrix. Another option is to maintain like a predecessor structure. So for every entry, you can say, which entry did I have to look at? Or as someone suggested, you could actually just start at the very top because that's the only thing you care about and just like walk down the table and figure out the choices. So you have these multiple methods of implementation, and the one that you want to use specifically depends on how you want to solve it. Yeah?
Would there ever be more than one true values for a given item? Like,
So the thing is, if these were equal, then you could do either.
okay. But there's no way of representing that.
You could actually put tuples there. You could say, you can actually set up like, you could do it. Technically, you can set up a DAG amongst these entries that tell you all paths in the DAGs are going to lead you. So yes, there are ways of representing that.
For the true-false case, there'd only be one.
There'd only be one, but but again, I think that let's end these questions because once I give you an example and you code it up, I think all of it will be crystal clear. Like you actually write the code and then it's like, okay, now you know what's going on. So I will give you a small homework, so I'm not going to give you too much time to do it. Maybe like less than a week or so, because it's really a small example. You should be able to code it up in a few hours. Yeah?
Can you post like some solved examples of this for us to study?
I mean, I thought this was it, but I guess maybe this doesn't count. So I'm going to do more. So yeah, I will put a book chapter of CLRS, and it has many solutions. But I'm going to talk about more dynamic programming solutions of this form. And yeah, I'll reference a book chapter. Let me try to put out this homework as soon as I can, and I want you guys to look at it, and then if there's still problems, then we can discuss more about it in the lecture. Okay. Okay. So we have only about 10 minutes left, but I'll just introduce another problem, which is a classic